Good morning. I'm Lauren Deason. I'm excited to be here kicking off this year's FlowCon, which was actually one of the first conferences that I attended when I was getting into cybersecurity several years back. And I learned a lot from this conference, and I believe I still even have my laminated bro cheat sheet hiding somewhere here in my desk. So it's pretty cool to be back here kicking off this conference, and also pretty cool that I didn't even have to change out of my sweatpants to do it. So that's a first. So I'm going to be talking to you today about this topic of the conference, using data to defend. But before I get into any more specifics on what I mean by that, a little bit of background on me. My educational background is in math and economics. Prior to working as a data scientist, I was focused on international trade, working at these various acronyms and institutions, and then was lucky enough to land a position as a data scientist on a research project for DARPA that focused on network defense and analyzing network and other cyber relevant logs to develop algorithms to detect malicious activity. And then for the past couple of years, I've been working for Facebook, supporting their community integrity team, where our focus is to prevent malicious actors from causing a wide variety of harms to both the company and the users and society more generally. And probably the most important thing to note about me is my unique ability to Photoshop pictures of my cat, Oliver, who I am unable to give a presentation without including in at least one slide, and you may see him again later. Okay, so turning back to defending with data. That's a pretty vague title, right? So what are we talking about defending? Well, the network, obviously. You all are in network defense. And so when we talk about defending the network, typically what we mean is that we're trying to defect some kind of critical infrastructure, maybe some intellectual property or sensitive business or customer data. But today, for the scope of this talk, I want to expand this definition a little bit and think about the ways in which we can apply some of the techniques that we already know to defending not just the network, but the social network. Yes, that one. So at a company like Facebook, we obviously still have the need to protect all of these standard network defense targets, the infrastructure, IP, sensitive data. But in addition, there's a few more dimensions that make some of the applications here somewhat unique in a social network environment. So specifically, we also might include in scope public trust and discourse in institutions. So you can think about malicious actors on a social networking platform engaging in impersonation or other deceptive behavior that might cause people to lose faith in public conversation or institutions, such as elections. We also are very concerned about offline physical safety. Which is something that can come into play from on-platform behavior, including hate speech or explicit incitement to violence, or things like human trafficking and child exploitation, which have very immediate and very real offline physical consequences. A few examples of specific attacks from the past that have happened either to Facebook, the company, or to users of Facebook and its family of apps, are highlighted here. So the first couple of headlines there, the spyware injected onto phones via WhatsApp, and the security bug in the second screenshot there was a security bug in a Facebook feature called View As that allowed you to click and see how your profile would appear to someone else, which had a vulnerability that allowed attackers to harvest credentials from a large number of users. Those two are examples of attacks that I would consider to be sort of in scope for traditional network defense, the kind of thing that any company is trying to protect against. The other ones that I list here, I think, are somewhat unique to the social network environment. So on the bottom left there, the headline about Facebook filing a lawsuit against Android app developers. In this particular case, there were a couple of developers that were taking advantage of a feature on Facebook called Facebook Audience Network, which allows developers to monetize their apps by showing Facebook ads within their product. And the way you monetize on that is based on the number of users who see or click on the ads. And what these developers had done was to inject a piece of code into their app, such that when users downloaded it, it appeared as though the user was clicking on the ads when they weren't. And so this kind of falls outside of the realm of what would traditionally be considered malware, in the sense that it's not doing a standard malware thing of trying to harvest credentials or connect to some command and control server, but rather it's just engaging in fake engagement with the Facebook platform. On the right-hand side, I've listed a couple more examples of malicious activity which aren't scripted like all the ones on the left are. So the top one is a screenshot from something called the Coordinated Inauthentic Behavior Report, which is a report that Facebook puts out every month to summarize the enforcement actions against actors who violate the policy against what we call coordinated inauthentic behavior. And what that is basically malicious actors coordinating with each other to deceive users for a variety of financial or political goals. The last example on the bottom right there is kind of, I would say, almost a meta example of malicious activity that's specific to social network, or at least the tech space, because what you're seeing there is an example of someone posting an ad to buy and sell what I would describe as illicit trade, because what they're buying and selling is actually an asset that it's not legal to buy and sell. In this case, the asset is a Google AdSense account. And so Google AdSense accounts you can think of as basically very similar to what I was describing a minute ago with the Facebook Audience Network. Developers or domain owners can monetize by showing Google ads on their site. In the case of, in order to show an ad, you have to have a Google AdSense account. And in order to get that account, your domain has to qualify by meeting certain criteria. So for example, it has to be sufficiently old. It has to have a history of posting benign content. And so as a result, there's a black market for these accounts, so that malicious actors who want to monetize off of using Google ads by posting clickbaity or violating content will have an incentive to purchase these ad accounts. So this is an example of a quote warmed, meaning that the domain has already been kind of built up a good reputation, of a warmed Google AdSense account that someone is posting for sale, and they're actually posting this on a Facebook group. So that's kind of the meta aspect I was getting at there. Okay, so that's what we're defending. Now I want to talk a little bit about what kinds of data can we use to defend in this context. Well, in the case of traditional network defense, there's this notion of PCAP, packet capture, as sort of the be-all, end-all ground truth for what happened on the network. And sometimes PCAP might be an input directly into some kind of classifier or detection algorithm, but more often it tends to be used as additional context or data to be looked at in a deep dive after some suspicious activity has already been flagged by some higher level alert. In the case of a social network environment, what would the analogous data type be here when we're thinking about some of those additional networks unique to defending the social network? Well, I think that something like user-generated content is in many ways analogous because it's kind of the most raw, granular form of data that we have. and in a similar way to PCAP, can be used as direct input to detection algorithms, but I would say perhaps even more often it's used the same way PCAP is, as sort of a ground truth way to verify whether or not something is violating or something is bad on the platform. So what I mean by user-generated content is things that look like this. So user posts, messages, and they could include videos, text, images, etc. And like I just mentioned, there are certainly cases where this raw granular data serves as an input directly into detection algorithms or classification algorithms. So obviously with all the natural language that's present on the platform, there are a lot of use cases for having this feed directly into classification algorithms. So a quick example of this would be Facebook's implementation of Google's word2vec natural language processing algorithm, where each word is mapped to a representation in an embedding space. At Facebook, because of the scale, obviously there's a lot of different languages that this needs to be trained on. But in addition, even within a given language, different regions and different markets differ from each other in terms of the languages that are used, and of course languages constantly evolving over time. So models like this need to be trained in a market-specific way and constantly updated. So this slide is showing you the nearest neighbors in the embedding space of these seed words in various markets, where you can see that even in markets that speak the same language, you get a variety of different text that is similar to happy birthday. Okay, coming back to this example slide I had a second ago, this looks like a fairly arbitrary mishmash of user-generated content, none of which appears immediately to be obviously malicious or policy violating. But in fact, every single one of these screenshots comes from one of those coordinated inauthentic behavior reports that I mentioned earlier, meaning that they were all posted by actors who violated the coordinated inauthentic behavior policy and were removed from the platform due to that violation. So the point here is that for certain violation types, such as coordinated inauthentic behavior, it can often be very difficult, if not impossible, to detect any kind of malicious activity from analyzing the most granular content level data, because that by itself, without additional context or without additional metadata, might not have any indication at all of violating behavior, of violating activity. So an analogy in the traditional network defense space, I would say, is something like data exfiltration, where if you're looking simply at the content of what is being transmitted across the wire, the contents of a file, if the file itself is not malware, something like data exfiltration is not going to be detectable by just looking at the pure contents, right? You need additional signals like the timing or the source and the destination of where the file is going. Okay. Which brings me to this question of the limitations of raw content level data. So I think in both the case of network and social networks, the two types of granular data I've described, PCAP and raw user-generated content, can be very useful as a source of final ground truth, but they often do have a limitation in terms of what they can pick up on in terms of certain violating behaviors. And in addition to that, as we know, they also have limitations in terms of scale, because these types of data take up a lot of storage space, as well as have a high computational cost if we're trying to run detection algorithms using them as input. And then finally, they also have larger privacy concerns than other types of more aggregated data because of sensitive data that might be contained therein. And we know that in both traditional network defense and also in the social network environment, we're seeing more and more of a move towards increased privacy and encryption. So in the case of network defense, of course, you're seeing more and more encrypted traffic across the wire. And similarly, For example, Facebook announced that all one-to-one messaging, including Facebook Messenger, will be fully encrypted in the future. So those limitations of the most granular kind of ground truth content level data are often cited as the motivation in traditional network defense for using NetFlow, which, of course, as everyone here knows, is a good source of is a good way to get around some of those limitations, and is in fact the basis of this entire conference, right? So, in the social network environment, what would be the equivalent? What would we think of as a standardized social NetFlow in the same way that you have a standardized or a mostly standardized description of NetFlow in traditional networking? Well, just like NetFlow contains information about the source and the destination of who is talking to who on a network and maybe how much they're saying to each other, in a social network environment, we similarly have representations of source and destination. And of course, we have probably a more diverse set of types of nodes and edges when this is represented as a graph, which is the natural representation, of course, for something like a social network, where we have users, but we also have nodes that might be groups or pages. And the edges that connect them, just like IPs are connected in NetFlow, are things like on-platform connections like friendships or adminning a page or joining a group, as well as other connection types that are based on infrastructure. So for example, devices using, accounts using the same device or being observed using the same browser are all connections that we can represent using this graph representation. And in the same in the same way that we can then apply a whole host of graph analytics to NetFlow, we can use this to detect behavior such as coordinated and authentic behavior mentioned earlier to find clusters of users who are interacting with each other and who are coordinating in order to deceive other users. Okay, so that was the what we're defending, what data we're using. And now I want to get to the more interesting part of how. Okay. So any defensive strategy using data, I think can be thought of as this kind of funnel where you're preventing malicious activity, or at least trying to detect or develop algorithms to detect what you failed to prevent, and then mitigating against that which you detect. In terms of how we use data to do this, I'm highlighting here detection because I think that's the piece of this where data really shines. Of course, detection feeds directly into mitigation and then also prevention. As you detect bad activity, you take mitigating actions as well as implement new preventative actions to prevent that from happening again in the future. So on the left, I've listed sort of what I consider the traditional network defense examples, and on the right, in the social networking context. Okay, so if we're focusing on detection with data, we can dive a little bit deeper and ask what kinds of algorithms are we using, are we feeding this data to in order to detect? And oftentimes people consider this sort of binary categorization between having rule-based detection or some more sophisticated, possibly black box machine learning-based detection. So let's take a closer look at those from both a traditional network and a social network perspective. In the rules-based category, in traditional network defense, you have access to things like Snort, Suricata, and Zeek that allow you to define specific rules or signatures that you can block or take action based on. And of course, at a company like Facebook, we have access to all of those as well. And then in addition, when we consider the additional dimensions that we care about, we might have other rule-based detection based on applied to user-generated content based on things like regular expressions for terms that are associated with violating content, like maybe illicit trade or harmful conspiracy theories like QAnon. And we can also have rules against specific user behavior observed in the data, like number of posts per time window to a given page to prevent spam. At the other end of the spectrum, instead of rules, we could feed all of our data to this friendly-looking robot over here who might run some kind of anomaly detection or clustering or supervised learning and give us back an answer as to whether what we're telling it is benign or malicious. More often, I think the value in a lot of the machine learning applications in this space aren't a simple binary classifier of benign versus malicious, but classifiers for some kind of more intermediate contextual data that can be used further down the line to make a decision or a classification. So for example, classifying traffic as a certain protocol in the case of network defense, or in the case of, at Facebook, a lot of the NLP classifications or topic classification can be an important application of machine learning that doesn't get directly at the question of whether or not a given actor or piece of content is malicious, but provides additional contextual data that's needed to make that decision. Okay, so at this conference, I suspect, being a research conference, most people here are probably more interested in one of these two categories versus the other. And I want to sort of make the point in the next examples that I give that there's a lot of value in both of these. And I think there's some really cool ways that people have shown recently to combine the best of both of these worlds together, specifically to use the latest AI and machine learning technology to learn complex relationships that exist in the data that a human can't see or can't process the volume of data necessary to come up with. But at the same time, still leveraging a lot of the human expertise and intuition that is baked into some of our simpler heuristics and rule-based methods. Okay, so specifically, I want to think about how we can use both of these to scale human expertise. And I want to motivate this by starting with an example from my team at work where we wanted to detect malicious actors using the following workflow that I'm going to describe to you that combines together multiple weak signals. So what I'm showing you here is an example of a standard Facebook account. This one happens to belong to my cat, Oliver. His middle name is Griffin. And let me start by telling you a few factoids about Oliver's account. So he has between 10 and 100 friends. He's been on Facebook for over 5 years, and he is not a member of any groups. So these little factoids, as I just called them, could each individually be considered very weak heuristics for whether or not this particular account is likely to be malicious or, say, a fake account developed to spam other people. So having a reasonably large or, say, normal number of friends and having been on the platform for over 5 years could both be considered heuristics for less likely to be malicious, whereas not being a member of any groups might be an indicator in the other direction. Obviously, none of these on their own are going to be very useful if you apply them across the entire universe of accounts to finding bad guys. But the point of this exercise is that if you have enough of these weak heuristics, maybe you can combine them together to find combinations of them that are unique enough to certain bad actors. So the hypothesis we had on my team was that if we started with a certain set of bad actors, in this case it was 50 pages that had been compromised and were being used for malicious, in this case financially motivated activity. If we had access to sort of a large repository of heuristics that humans had encoded into rules like the ones I just described, maybe we could run a rule mining algorithm to learn what combinations of these heuristics are unique to this set and then use that to find more bad actors. So what we did was to take advantage of the fact that there is, in fact, such a repository of heuristics at Facebook, not necessarily intended for this particular process, but you can think of it as a system of text tags, basically, that different teams across the company use to track different features about accounts or entities on the Facebook graph that they care about. So things like having between 10 and 100 friends, having been on Facebook for more than 5 years, etc. Okay. So what we did was to take our seed set of 50 bad accounts of malicious, or in this case, compromised pages, and treat that as our positive set, and then grab a large sample of benign pages, pull all of the heuristics from those, and then run a high precision rule mining algorithm to learn what combinations of these heuristics end up being high precision indicators for this seed set relative to the negative set. And in fact, this worked very well. We came up with a list of rules and then went back and queried the data to say, are there any other pages that match these combinations of heuristics? And in fact, there were, and this surfaced several additional pages that turned out to have been hacked upon further review. Okay, so all of this is leading up to sort of a more generalized idea of encoding human expertise in a way that we can scale this up to improve some of our machine learning techniques. So specifically, I want to describe here the overall problem of what some people call overcoming the labeling bottleneck. What this is referring to is the fact that a lot of the latest and greatest ML techniques only work really well when you have a large volume of labeled data to train them with, right? So of course there's some exceptions to this. Transfer learning is having a lot of success in various use cases, but there's certain problem spaces where you really do need a large volume of labeled data and where that is not easy to acquire. So for example, think of hate speech, for example. Identifying a given phrase or post as classified as hate speech requires some amount of subjective human assessment, which is very costly to acquire at large scale. And it's also something that hate speech is something that can change and evolve over time. And so there's kind of a constant need for a constant source of this large volume of scaled data. So what this plot is trying to show is a range of strategies for getting a large volume of labeled data. So on the left-hand side, or the leftmost part of the x-axis, is referring to fully automated labels, where you have a way to just instruct a machine to ingest a bunch of unlabeled data and follow some logic to assign labels to them. That's obviously the least costly in terms of human resources way to get labels, but also obviously probably the most error prone because we don't have a specific set of easily programmable logic to correctly label all of the samples. Otherwise, we wouldn't need a machine learning algorithm to begin with, right? And then on the right-hand side, you have the other extreme where everything is fully human labeled. So without going into too much detail of the different categories here, we can get to any of them in the Q&A section if people have specific questions. I'm going to focus in the next few examples primarily on the left half of this, specifically in the weakly supervised category, where it's similar to what I just described in terms of having a machine do all the labeling for us. But we're going to take advantage of some algorithms that allow us to combine together multiple simple heuristics, such as the ones I just described in the previous slide, to generate probabilistic labels that are automatically generated, but take into account correlations and dependencies or disagreement rates between the heuristics that you feed it, in order to come up with one final label for a given sample. So open source tools like Snorkel do this for you. And so I'm going to give an example initially from the InfoSec space from FireEye. And this is a tool that I saw presented at a conference a couple of years ago that's useful for malware analysis that leverages this Snorkel tool. So let me describe the specific use case here, and then I'll describe how they take advantage of programmatic labeling to improve their classifier. So in the malware space, a human malware analyst's job is often to take a given file and then determine if it's malicious or not. And one of the tools they have in their toolbox is to run this program called strings against the file. And what this program does is simply take in the file, which is just, a sequence of bytes, so a sequence of zeros and ones, which could represent all kinds of different things, including data or instructions. Some of those bytes typically are intended to represent text, and the numeric values of the bytes represent either the ASCII or the Unicode character in the text. So what strings does is it attempts to extract any sequences of bytes that are likely or might represent strings or human readable characters, and it extracts those and dumps them out to a list like the one you see on the right. So you can see that this generates some pieces of human readable text, like this program cannot be run in DOS mode, etc. And the analyst can kind of browse through this and be on the lookout for specific strings that are suspicious to them or indicative of potential malware. In addition to human readable strings, you see on the bottom left of the picture on the right, though, that there's also kind of a fair amount of garbage, which is expected because, remember, the input file is just a bunch of zeros and ones, and the way strings is figuring out if something is meant to represent characters or not is simply by the character that's used to terminate the sequence of, the byte value that's used to terminate the sequence of characters, which can appear outside of strings as well. So the key takeaway here is that this program gives you all the strings that appear in the file, but it also gives you a fair amount of garbage. So what FireEye's string sifter model aims to do is to take the output of this strings file and rank it in a way that the most likely relevant strings, meaning relevant for a malware analyst, get floated to the top and everything else gets pushed down the list. So their classification model is actually what they call a learning to rank model. It's basically assigning a score to each string as it gets output. And so rather than focus on the model here, I want to focus on how do they get the volume of training data that they need in order to get good results from this model. So they use this tool I just mentioned called Snorkel, where basically they're able to have their malware analysts who have the subject matter expertise and have certain heuristics in mind. So for example, they might know that if a certain regular expression appears in a string, that's more likely to be malicious. Or if a string contains only numbers and no letters, then it's probably more likely to be irrelevant to the malware analyst. So by encoding a bunch of heuristics like that, Snorkel is able to take those heuristics, apply them to a large set of files, or the output of strings on a large set of files, and then learn the correlations and dependencies between the different heuristics to sort of downweight the ones that aren't very good, meaning that they don't tend to agree with other heuristics a lot, and give more weight to the ones that seem pretty good. And this then allows it to combine together all the heuristics into one final label for each piece of unlabeled data. And now you have a large volume of labeled data, which still, isn't going to be as precise as you want for your final output of your classifier, but which you can feed into a classifier that itself takes into account a much richer set of input features to then train the model and produce a prediction for ranking these strings. Okay. A very similar example from a couple of teams at Facebook that have used something like the Snorkel tool to programmatically label data to improve classification. It comes from a couple of teams that focus on detecting violating content in the realm of militant social movements, which are basically groups on Facebook that explicitly declare an intent to be violent and organize as a militia, which will cause them to be removed from the platform. And another team that focuses on illicit trade, including drugs and firearms. So in both of these problem spaces, there's a need to automatically detect content or actors who are posting content that violates these policies. And as I mentioned before, this can be a difficult problem because of the need for large volumes of labeled data. And again, the fact that what would be considered a true positive here might be changing over time, as in these cases, actors might use a lot of code words, for example, to evade detection. And they can easily adapt to new code words once the old ones are detected by Facebook. So it's important to have the machine learning models here constantly being retrained, which requires large volumes of data. So in the same way that was done in the previous example, in both of these cases, human subject matter experts were able to encode some basic heuristics for whether or not a piece of content is likely to violate one of these policies. So for example, maybe regular expressions for certain phrases that are known to be associated with these, or something like a connection on the graph to another actor who has already been taken down for violating one of these policies. And those heuristics are then combined together intelligently by Snorkel to produce a label on a large volume of unlabeled data, which can then be refed back in to a classification model that itself takes into account a much richer set of features. Okay, so I've kind of glossed over so far in these past two examples what the actual classification model looks like. I've just been kind of talking about how do we get the large volume of labeled data that we need to get good results from the model. So in this drug content example, the model that it uses to take in all this large volume of labeled data is a deep learning model that uses something called multimodal deep learning. So if you're not familiar with multimodal deep learning, this slide here, I think, is a nice introduction to the concept. A multimodal learning model is one that takes in multiple modalities of data. And a modality here you can just think of as a piece of input data that is perceived in different ways by a human. So for example, text is one modality, image is one modality, and of course you can have others as well. But this example here comes from Facebook's Hateful Memes Challenge, which is a coding challenge which I believe is still open, which is attempting to have people build models to detect hate speech, where the input is a combination of an image and text. The particular examples here are toned down. They're not actual hate speech. I believe they call them mean speech. But you can see very clearly the importance of a model for this particular use case, learning from both the image and the text in order to produce a final classification decision. Whereas if you had separate models, one using just the images and one looking just at text and then trying to combine them, wouldn't be very useful, because as this shows, you have the same text and images across the top and bottom rows, but different desired classification outcomes, where the first one is mean speech, the second one is nice speech, I guess, and the third one is maybe just benign speech. So going back to the drug content example, the modalities that were used in that model, similar to the way we have text and image here, actually uses both of those if there's images in the post, and then it also has additional modalities that include things like comments or interactions from other users. And so that rich feature set is taken in and applied to that large volume of labeled data I mentioned a second ago. One of the main sort of implementations of multimodal deep learning is the case where you have images and text, but different than this hate speech example here. A classic use case is where you have an image and you're trying to associate it with a label that describes what's in the image. So one way to accomplish this would be with a standard multi-class classifier. But what's been shown recently is that using a multimodal model where you're feeding in both the image as one input and the natural language text as the other input, and learning a joint embedding or learning embeddings for both the image and the text at the same time can actually give you really good results because it's allowing the model to learn relationships between similar words at the same time as relationships between similar images in a way that you don't get if you run these two things separately. And so a really cool application of multimodal deep learning that I saw presented by researchers at Sophos is this example right here, again in the malware space, where they're kind of taking this idea of using a multimodal classifier that's trying to match an image with the label or the text that represents the image. And in this case, instead of an image, the input is a file. So just, again, a static representation of the sequence of zeros and ones that make up a given file. And in this classification problem, they're not trying to get to a binary indicator of malicious or benign. Rather, for a given piece of malware, their goal is to assign the correct tags. So similar to the image labeling problem, here they want to assign to a given binary file a set of tags that describes what kind of malware this is. So you can see in the top left image there a few examples of the different tags they have: adware, downloader, spyware, etc. And so the way they build this model is portrayed in the bottom left. This is a deep learning model where you're feeding in both the binary representation of the file and one hot encoded version or representation of the tag or tags that are applied to the file. And then having the model learn, and basically it's going to generate an embedding representation of the file and an embedding representation of the set of tags in the same dimensional space, so that tags that apply to that given file should have an embedding that's very, very close to that of the file in this embedding space. And that's in fact what you see on the right. This is a t-SNE representation, a two-dimensional representation of the embeddings that are generated by this model, where the larger icons represent the embedding of the tags themselves, and the smaller icons represent the embeddings of the files that are labeled with those various tags. So I think this is a really cool application of multimodal deep learning to the InfoSec space. And moreover, the part about it that I haven't told you is how they generate the labels for this problem. And as you may have guessed, it uses some form of programmatic labeling similar to what I was describing a minute ago. In this case, what they do is they actually extract tokens from descriptions of the various files that come from various antivirus vendors. And then they use human expertise to map from these tokens to these different categories of malware tags. So this is an example of basically using these heuristics or these weak labeling functions and then combining them in an intelligent way that takes into account the correlations and dependencies of these heuristics on each other to then assign a final label. In this case, I don't believe they use Snorkel, but they developed their own algorithm for combining together these multiple weak labeling functions. Okay, so what am I hoping that people get out of this talk? Well, one of the main ideas here is simply that there is, I think, a pretty clear analogy to be made between traditional network defense and then some additional dimensions of network defense that apply uniquely in a social networking context. And so I'm hoping you can all think about some of your research and ways that it could be applied across problem spaces. I also wanted to highlight this notion of combining together weak signals in order to yield high precision results. And then beyond that, the fact that these open source tools like Snorkel exist to help you take a large volume of sort of simple heuristics or human expertise that has somehow been encoded into simple logic, and generate reasonably good labels with them that can be fed into any kind of downstream classifier that you're trying to train. There's a paper I came across called Snorkel Drybell from Google Research, which is basically a framework for how large-scale companies with a large volume of sort of institutional knowledge, maybe embedded in different kinds of repositories, can be extracted and then fed into a tool like Snorkel in order to do this. And then finally, the idea of using different modalities or multimodal learning models is, I think, already very interesting on its own, but particularly when combined with this notion of using weak labels as a way to generate something like text tags or labels that could themselves be used as one modality, as an additional modality to whatever kind of data you have, whether it's image, a binary file, or anything else. So I encourage you to kind of think about, at your particular company or place of work, what forms of encoded human expertise might already exist that that people haven't thought about leveraging in this way. So things like snort rules, suricata rules that you have, or like alerts that you have that you don't pay attention to because they're too noisy. All of these things embed some amount of human expertise as heuristics that point towards behavior that you do care about detecting. So I think there's probably a lot to be done out there in terms of gathering some of this human expertise and using it in this way to feed into more black box machine learning models. Okay, the last couple of slides just have a bunch of links and references to several of the articles and research papers that I mentioned earlier. So I will share these with everyone here, and I look forward to chatting with you.
Thanks for sharing this great insights, Dr. Deason. We've got a number of great questions that have come in, so I'm just going to pop over to the side here and snag some of those up to share with you. So a couple of questions that sort of shared a common theme from Bahiria, Jim, and Ed, talking about the rule mining algorithm that you use to extract those rules. So there was a question about clustering on the features that you observe in the rules. You know, how would you approach maybe looking at the features rather than just individually applying rules and using the mined rules? And then, of course, some question on digging a little bit more deeply into what sort of rule mining algorithm you used, whether the process ends up being proprietary to you over there at Facebook or if there's some more general approach. So I'll start off with those.
Yeah, thank you so much. And thanks for all the questions. So in terms of the specific rule mining algorithm, it was implemented by someone at Facebook. So I presume the actual implementation of it is proprietary. But I'll post a link in the Discord to a public research page of the engineer who wrote that, who has some research papers, I think, that are closely related to the algorithm. At a high level, the algorithm, the way that it works is it takes in the set of features that you give it, and it's basically building a tree, and it's doing a depth-first search to ask the question of the seed set that you feed it, what is the maximum precision that I can get using combinations of these features for the seed set relative to the negative set that you fed it. And of course, there's some hyperparameters you can feed it in terms of the number of different features that it's allowed to combine into a specific rule. I want to say that the motivation initially for this particular algorithm was a use case where you have something that you're looking for that's very low prevalence relative to the rest of the population. So some kind of violating content. I believe the specific motivating example that I saw it applied to was detecting inappropriate speech in a certain context. And so being applied to natural language, where the inputs are actually just tokens of natural language, this kind of gets at the question about clustering versus rule mining. When you have an extremely large universe of tokens, right? There are, of course, nearest neighbor kinds of searches you can do, not on the tokens themselves, maybe on some kind of embedding representation of the tokens. But the other big consideration here is this question of prevalence. If the thing that we're looking for is expected to be extremely low prevalence in the population, oftentimes clustering techniques where we're taking into account these features that in that particular example would be for them, is to kind of bootstrap, not get a holistic sort of representation based on input features of what the malicious activity looks like in this feature space, but rather just find more examples of violating activity. So that's the whole sort of motivation behind the high precision part of it. It's not intended to have high recall at all. It's not intended to sort of be a representative characterization of what input features holistically sort of represent this kind of bad behavior. But instead, it's meant to identify certain terms, right, certain tokens that are used in examples of violating speech that you can then go easily query for, find more of them on the graph, and then kind of similar in terms of how I was suggesting using the programmatic labeling, use those as kind of additional labeled examples to then possibly run more sophisticated algorithms like clustering on, in the case of natural language, perhaps some kind of embedding representation to learn more complex relationships between the things in your true positive set and your true negative set. I think there was also a question on the size of the seed set. And so to give a little bit more detail on that, I mentioned that the way the algorithm works is to create this tree representation and then find the highest precision sort of path to the node, or sorry, to the highest precision combination of input features that cover the highest percentage of your seed set. And then the way the algorithm works is once it defines that first rule, it removes from your set all of the things that are covered by that rule, and then it repeats on whatever is remaining in the seed set. So in this way, it kind of tries to iteratively cover your seed set by finding combinations of input features that cover as many things as possible in the seed set, and then moving on to the next batch. And because of that, the seed set doesn't need to be incredibly large. The most important thing here is the size of your negative sample. And so in the case that I was applying it to, I was using roughly 10 million negative examples just randomly sampled from the graph, whereas the seed set can be quite small in the tens or hundreds. And in fact, the larger the seed set is, depending on how homogeneous your seed set is, it might take the algorithm a long time to generate enough rules to cover the entire seed set. So you actually don't want it to be too large unless your seed set is very homogeneous in terms of the input features you're feeding.
Okay, thanks. Actually, if you don't mind, I wanted to dig in just a little bit to a thing that you said. So one of the interesting challenges that comes up a lot in NetFlow is, what's baseline data, right? What's expected to be benign. So you said sort of tens or hundreds of positive examples of the behavior that you're trying to identify and exclude, and you said you pulled 10 million negative examples. How do you come up with sufficiently high confidence rate that those are all negative examples and that you're not muddying the water, by including a couple of hundreds of the bad guys to overwhelm?
Yeah, so it really depends on the particular problem space, I guess, as to what your prior is to what the true prevalence of the thing in the population is. In certain cases like spam, yeah, there is some estimated prevalence that we have somewhere that we could incorporate. In other cases, like information operations, where you have very sophisticated actors that are well funded conducting these operations, I think there's reasonable assumptions to be made that it is near zero, and that if you're randomly sampling the population, you're unlikely to hit one of these things. But I think that the other part of that question, sort of how do you deal with this risk that there are some of those in your negative sample? This particular algorithm, right, is going to be attempting to find the highest precision combinations it can. So even if there are some false, let's say some false negatives in your negative sample set that are mislabeled, it is still going to be able to learn rules associated with the true positive set. It will just have a lower estimate of the precision, right? Because it will be treating those things that should be positives as negatives. But that is something you need to keep in mind when you're defining the negative set, and define it as narrowly as you possibly can to have it represent what you expect to actually be the true negatives in your use case.
Okay, great. Thanks for that response. You mentioned actors that have sophistication and budget, so I'm going to pick up Christian's question here, asking about the limitations of programmatic labeling and your thoughts on using this approach to help the analysis of an APT, which is coming with from a lot of different vectors, for sure.
Yeah, I think so. This programmatic labeling approach, I think, can be really powerful. I think one of the main, not limitations maybe, but sort of obstacles to being able to implement it is having sort of a well-defined framework to encode some of what I've been referring to as this human intuition, right? So in the case of the string sifter example from FireEye that I mentioned, experts were able to encode into, say, Python functions like, here's specific regular expressions that I know to be associated with strings that are often part of malware, or certain ones that are very likely to be part of benign files. And you do need a reasonably large volume of these weak labeling functions. So one thing is having a framework to programmatically encode this. And another thing is if you have more than one subject matter expert in this area, kind of aligning on definitions of true positives, and also entity resolution level. What exactly is the thing you're defining? In the case of APTs and looking at NetFlow data, right? Are you looking at the IP level? Are you looking at an IP pair? So figuring out the resolution at which you want to programmatically label things to then feed into a classifier, I think are important, like initial steps in order to being able to leverage this.
Okay, thanks very much for that answer. We are coming to the end of our question and answer time. There are still a handful of outstanding questions, so I would encourage everybody to continue the conversation over in Discord. Some of these questions are already posted there, so I'm excited to see what the community has to say and what Dr. Deason's responses are. Thank you so much for joining us and for giving us this keynote presentation.